All right, hi everyone. So we are going to dive a little bit deeper with derivatives and now start doing some applications of derivatives. So the first application of derivatives that we're going to talk about is called L'Hopital's rule. So I'm going to show you guys why L'Hopital's rule can be kind of cool and save us some work before I actually tell you even what it is. So if you remember back to our limits chapter, when we would do a problem like this, the limit as x approaches negative 2, x squared plus 3x plus 2 over x plus 2. The first thing we always try to do with a limit is we substitute in the value, right? So negative 2 squared would give me 4, and then minus 6 plus 2. So I would get 0 on the top, and I would get 0 on the bottom. So we didn't actually talk about this when we did it, or if I did, we did it very briefly, but this is called indeterminate form. Okay, so 0 over 0, that's a problem for us, and we already know that, so we didn't really talk too much about it, but I want to give you the name of it because I'm going to be talking about it a lot more in this chapter. So anytime we had something like that, we thought about our different tricks. We could factor, do a conjugate, all that good stuff. So for this one, we're of course going to factor. The limit as x approaches negative 2 of x plus 2 times x plus 1 over x plus 2. We're going to cancel those factors to be left with the limit as x approaches negative 2 of x plus 1. And now we can substitute our value in, and we would get negative 2 plus 1, which we know is negative 1. All right. For the next one, let's think about plugging 0 in there, and we would get 1 plus 0, which is 1, square root of 1 minus 1. So we would get 0 on the top and 0 on the bottom. So again, there's our indeterminate form. All right, that's how we kind of knew that we had a problem and we had to try something else. So for this one, we multiplied by the conjugate. So the limit as x approaches 0 of the square root of 1 plus x minus 1 over x times the conjugate, which is the square root of 1 plus x plus 1 over the square root of 1 plus x plus 1. All right, and if we start to simplify that, we know we can multiply the top, and the middle terms are going to cancel. So we're just left with 1 plus x and then minus 1. And on the bottom, we're going to leave it alone. So x times the square root of 1 plus x plus 1. Oops, I made that bar very long. When we look at this, we can see that those 1's are going to cancel each other. So we have the limit as x approaches 0 of x over x times the square root of 1 plus x plus 1. That needs parentheses there. And those x's will actually cancel to leave us with a 1. So now we have the limit as x approaches 0 of 1 over the square root of 1 plus x plus 1. And now if we substitute the 0 in there, we actually get 1 over 2. We get 1/2. Okay? But multiplying by a conjugate can get messy and get annoying. So now we're actually going to talk about L'Hopital's rule. So L'Hôpital, by the way, is actually French for the hospital. It's also some dude's name. All right, he was the dude that kind of discovered all of this. But it does actually mean hospital. So if you are trying to plug in numbers into your limit and you get either 0 over 0, so our first indeterminate form that we just talked about with both of these, or if you get infinity over infinity, that's another form of another indeterminate form. Indeterminate form. Anytime you get one of those as your limit, you can take the derivative of the numerator and denominator separately. All right, we're not doing quotient rule. We're doing the limit, or I'm sorry, we're doing the derivative of the numerator and the derivative of the denominator completely separate. And then we're going to try and take the limit again. So we're not getting rid of the limit. We're not, magically making that disappear. We're just doing the derivative of the numerator, the derivative of the denominator, and then we're going to try and take the limit again. But this only applies if you get indeterminate form when you do substitution first. All right, so anytime you get indeterminate form, Ms. Vazda always says that you're taking your limit to the hospital, right? L'Hopital. Haha. So you have a problem with it, you're taking it to the hospital. You're applying L'Hopital's rule. So if we do the limit as x approaches 0 of sine of x over x, and we try and substitute, sine of 0 is 0, and then x would be 0. So that's our indeterminate form. That's how we know we can apply L'Hopital's rule. So the limit as x approaches 0, and now we're going to actually apply L'Hopital's. So the derivative of sine is just cosine of x, and the derivative of x is just 1. Now we're going to try and actually substitute again. So the cosine of 0 is 1, and on the bottom we have 1. So 1 over 1 tells us that this limit is actually just 1. Now this is a limit that we weren't able to do before because there was nothing algebraically to do. We can't factor, there's no conjugates, it's already got a common denominator. Like there was nothing to do, we were stuck. The only way we could get that limit was with our calculator. But now thanks to L'Hopital, we can actually find the limit by hand. All right, so if you notice, these first two examples are actually the two examples that we did up here. So I'm going to show you how quick they can be by applying L'Hopital's rule. So we already know that if we substitute this in, we would get 0 over 0. So if we apply L'Hopital, we'd get the limit as x approaches negative 2. The derivative of the top is 2x plus 3, and the derivative of the bottom is 1. Now if I substitute in, I'd have 2 times negative 2 plus 3, and I get that this overall limit is negative 1. Much faster than the first way I showed you. No factoring involved, no algebraing involved, right? So, much faster. Now let's look at the second one. We already know that if we substitute in 0, we would get 0 over 0, which is our indeterminate form. And so we want to apply L'Hopital's rule. The thing we want to remember real fast, the square root of 1 plus x is the same as 1 plus x to the 1/2 power. So if we go to take the derivative of that, we're going to have the limit as x approaches 0 of 1/2 times 1 plus x to the negative 1/2. The derivative of negative 1 is just 0, so that drops off. And then over the derivative of the bottom, which is 1. Now if I were you guys, I would take a second and simplify this because fractions and fractions with negative exponents, like it's all really ugly. So I would rewrite this as the limit as x approaches 0 of, remember, negative exponent, drop it like it's hot. So 1 over 2, and then it's a square root of 1 plus x. Okay? Now that's much easier to evaluate. Now if I substitute that 0 in there, I get 1 over 2. So my limit is 1/2. And again, that's exactly what I got up here, and I didn't have to multiply by the conjugate. Look at how much simpler this is than what we did up here. Okay? All right, let's look at one that we haven't done yet. So now we're going to look at the limit as x approaches pi over 2 of secant x over 1 plus tangent x. Well, secant of x, we have to remember, is the same as 1 over cosine of x. All right, so if we start to substitute pi over 2, well, the cosine of pi over 2 is 0, so we'd get 1 over 0, which is a problem. But if we think about what that graph looks like, we know that at pi over 2, that graph is actually approaching infinity. Okay? Then if we look at the bottom, 1 plus tangent of x, the tangent function always has asymptotes at pi over 2. So that is also approaching infinity. This is our other indeterminate form, infinity over infinity. All right, so that's how we know we can apply L'Hopital's rule. So the limit as x approaches pi over 2, and we're going to take the derivative of the numerator and the derivative of the denominator. So the derivative of secant x is secant x times tangent x. And the derivative of 1 plus tangent x is secant squared x. All right, we can cancel one of those secant x's, so the limit as x approaches pi over 2 And now we have tangent x over secant x. And now we're going to try and evaluate that limit again. So the limit now, as we approach pi over 2, that's still infinity on the top, and it's still infinity on the bottom. So that's still a problem for us, right? But if we keep taking the derivative over and over again with secant and tangent, it's not going to get us anywhere because they're always just going to be there and switch places. So instead, once we get to here, now we're actually going to apply some algebra stuff. So now we're going to look at the limit as x approaches pi over 2. And I'm going to rewrite tangent as sine of x over cosine of x. And I'm going to rewrite secant as 1 over cosine x. Because when I do that, I can look at it then and see that the cosine x's are going to cancel each other, which means I'm left with the limit as x approaches pi over 2 of sine of x. And now I can try to evaluate. I know that the sine of pi over 2 is just 1. All right, so this was an example where we applied L'Hopital's rule and got to something that we could actually then simplify algebraically. So it kind of combined the two things that we know. All right, let's take a look at the next one. Limit as x approaches infinity of e to the 2x, that would give me infinity on the top, and 2x squared, that would give me infinity on the bottom. So there's my indeterminate form. That's how I know I can apply L'Hopital's rule. So the limit as x approaches infinity, and I'm going to take the derivative. The derivative of e to the 2x is e to the 2x, and then multiply by the derivative, so a 2, and I'm going to stick it in front. And then 2x squared, if I take that derivative, I'd actually get 4x. So I can simplify this down to the limit as x approaches infinity of e to the 2x over 2x. And now I can try and evaluate my limit again. So if I plug in infinity, I'd have infinity on the top, and I would have infinity on the bottom. That's still my indeterminate form, so now I'm going to do it again. All right, now if I do the limit as x approaches infinity and take the derivative of e to the 2x, I'd have the same thing, right? 2 e to the 2x, because I'd have e to the 2x times the derivative. And then on the bottom, I would have just 2. Well, now if I evaluate my limit, or actually, sorry, those 2's cancel. Limit as x approaches infinity of e to the 2x. Well, I know that as x approaches infinity, this gets bigger and bigger. It grows to infinity. So that is actually my limit. Now, it would be infinity over 1, right? On the bottom, we would have a 1. That's why it's not indeterminate form, because indeterminate form would be infinity over infinity. This one, the denominator actually canceled to be a 1. So having infinity, that's okay. We have limits that are infinity sometimes. So don't get thrown off by that. Okay, 2 quick things to talk about. First things first, just because we can use L'Hopital's rule doesn't mean that we should every single time. So we can try it, and it's going to get us to the right answer, but sometimes there are other things that make more sense. So when we look at this, the limit as x approaches infinity, if we look at all of this, if I plug in infinity, I'm going to be getting infinity over infinity. So I know that I can use L'Hopital's rule, which is good. So if I go ahead and do it, the limit as x approaches infinity, the derivative of the top is going to be 12x squared plus 10x minus 6 over 12x to the third, 12x to the third, plus 18x squared minus 14x. And if I plug in infinity, it's still indeterminate form, so I have to do it again. The limit as x approaches infinity of 24x plus 10 over 36x squared plus 36x minus 14. And I'd still have infinity over infinity. So now I got to do it again. The limit as x approaches infinity of 24 over 72x plus 36. Well, now at least, if I plug in infinity, I'd have 24 over infinity, which if we think back to our limits chapter, we know that 24 divided by a super, super big number is actually going to give us 0. So we get that the limit is 0, which is good. But let me remind you that we learned about limit rules back in chapter 1. All right, when x approaches infinity, we only need to look at the highest powers. And think about the end behavior. All right, so when we look at the highest powers, we would actually have 4x to the third over 3x to the fourth. So we would simplify that down to 4 over 3x, which means we'd be looking at the limit as x approaches infinity of 4 over 3x, which gives us 4 over infinity, which we know is 0. If we think about the end behavior of that function, we get the answer much faster, right? When we look at this, it's bottom heavy. Even without plugging in infinity, I know that that has a horizontal asymptote at 0, and I don't have to take the derivative 5 times, right? And imagine if this function wasn't just a polynomial, right? You're doing all that work for nothing. So just because we have a new rule doesn't mean the old stuff goes away, okay? The very last thing I want to talk to you about is something that you need to be very, very careful of, okay? When we look at the limit as x approaches 3 of 1 over x minus 3, that equals 1 over 0. That is not an indeterminate form. And so L'Hopital's rule doesn't apply. Remember, in order to apply L'Hopital's rule, it has to be 0 over 0 or infinity over infinity. 1 over 0 just means it doesn't exist. Doesn't mean that it's indeterminate form. So when we're thinking about this limit, this is when we had to think about what that graph would look like. So we'd have a vertical asymptote at 3. And since it's a positive leading coefficient, we'd be going down on the left and up on the right. And so we know that this limit actually doesn't exist, because the limit on the left and the right don't equal each other. Now, if you mistakenly did L'Hopital, let's see what happens. We would get the limit as x approaches 3 of 1, the derivative of 1 would be 0 over the derivative of x minus 3, which is 1. We would get that the limit is actually 0. But we know that that doesn't even make sense because the limit doesn't exist. So not only does L'Hopital not apply in this instance, but if you do it, you get it wrong. So please, please, please be careful. That is the wrong limit. So it's not just, oh, you applied it and you shouldn't have. You applied it and you got the wrong answer. So be careful of that. All right, we're going to do tons of practice when I see you guys in class.